Welcome to The Explainer. Today, we're going to get our hands dirty with some absolutely incredible mechanical engineering. We are diving into the flight control system of the legendary F-15 Eagle, which is, and this is the amazing part, a total masterpiece designed to fly perfectly without a single computer helping out.
Okay, let's just start with this. This one sentence. This was the huge challenge the U.S. Air Force threw down for the F-15's designers. Think about that. No electronic safety net, no digital co-pilot. This jet had to fly and fly well, based on pure, old-school hydromechanical genius. So what in the world did the Air Force actually mean by Level 2 handling? It's not just some piece of jargon. It's a super precise definition of how a plane feels and performs in a pilot's hands when things get real. Right, so these military specs are kind of the gold standard. Level I, that's perfect, a dream to fly. Level 3 means, yeah, you can probably land it, but the mission's a total bust. Level 2, which was the target for the F-15's raw mechanical system, means a pilot can absolutely complete a tough air superiority mission, but, they're going to have to work for it a little bit. And this is what really puts the F-15's achievement into perspective. Its older brother, the legendary F-4 Phantom, couldn't even hit that Level 2 standard with all of its electronic stability systems helping out. The F-15 had to nail it with just levers, push rods, and hydraulics. It's kind of mind-blowing. So, how on earth did they pull that off? Well, the secret is this brilliantly complex device with, you gotta love it, a very government-sounding name, the Control Stick Boost and Pitch Compensator. Or let's just call it the CSBPC. Honestly, the best way to think about this thing is as a mechanical computer sitting right at the heart of the aircraft. It's the central hub that takes every tiny little movement of the pilot's stick and turns it into a precise, predictable action by the wings and tail. So inside this brain, you've got two key parts doing all the heavy lifting, the PRCA and the ARI. Together, they're constantly sensing the flight conditions and what the pilot is doing to make sure the plane responds the same way, whether it's just cruising along or pulling a crazy high G-turn in a dogfight. But a brain is pretty useless if it doesn't have muscles to carry out its commands. And for the F-15, that muscle comes from an incredibly tough and redundant hydraulic system. See, the jet isn't just powered by one hydraulic system. It has three totally separate ones. Power Control 1 runs off the left engine, Power Control 2 runs off the right, and then there's a third utility system that has pumps on both engines. We're talking layers upon layers of backup. And the result of all that? The F-15 can have a complete, catastrophic failure of any two of its three hydraulic systems and still be flown and landed safely. I mean, that level of reliability is it's staggering. This layered approach is really how they pull off that incredible redundancy. So you've got PC-1 and PC-2 handling opposite sides of the jet, but look, they both power the stabilators that control your pitch, which is critical. Then the utility system can step in and back up absolutely everything, and it's also the main power source for that mechanical brain. Okay, so we've got the brain and we've got the muscle, but how do they work together to create that perfect, intuitive control that fighter pilots just rave about? How does the F-15 actually feel to fly? Well, when a pilot pulls back on the stick, it's not just a simple lever. It kicks off this whole sophisticated mechanical dance. The PRCA adjusts how much the surfaces move based on how fast you're going. Hydraulics give it a boost so it feels effortless. And then a mixer makes sure all the right surfaces move in perfect harmony. And all of that crazy complexity, it creates this beautifully simple result for the person in the cockpit. It gives them a constant, reliable feel. So pulling 1G feels the same no matter your speed. The stick doesn't wander all over the place. It even automatically cancels out little changes when you pop the speed brakes or drop the flaps. And here's one more super clever design choice. The part that actually gives the pilot that force feedback, that feel, it's not way back in the tail like on most planes. They put it directly under the control stick. And that means less linkage, less slop, and a much more direct, crisp connection between the pilot and the plane. The entire design philosophy really came down to one critical thing. No matter what goes wrong, no matter what breaks, the pilot has to be able to fly the plane and bring it home, period. So even if the brains of the system, the PRCA, completely loses hydraulic power, it doesn't just fail in some catastrophic way. Nope. It automatically locks itself into a preset basic mechanical mode. The system literally simplifies itself, giving the pilot safe,
predictable control to get back on the ground.
And the system is just packed with these genius safety nets. There are safety springs that let a pilot literally muscle past a jammed linkage. You've got dual trim to stop a surface from getting stuck in some dangerous position. Even the control surfaces themselves are designed so that if they lose all power, they just naturally flutter into a neutral, safe position. Ultimately, it's not magic. It's the result of all this meticulous mechanical engineering that leads to the highest compliment a pilot can ever give a plane. They might not know all the details about the PRCA or the triple redundant hydraulics, but they know one thing for sure. It just feels good.
And this all brings up a really fascinating final question, right? If a purely hydromechanical system can be this capable, this reliable, and feel this good to fly, what was the point of adding computers later? What more could electronics possibly bring to the table? Well, that is a story for another time.